So we began our discussion of discussing how to represent concentrations of a solution. And in the last video, we were talking about percentage concentrations. Let's talk about a concentration that's perhaps the most widely used in whole of chemistry, and it's called the molarity. It's represented in units called molars, and it's represented by capital M. Uh, its unit is molar. Now, molarity just means is you take moles of solute particles, moles of solute, over liters of solution. So this ratio is called the molarity. The molarity. So for instance, let's say let's take an example to understand this. Let's say you had 100 grams of calcium carbonate, or let's take 50 grams. So let's say you had 50 grams of calcium carbonate dissolved in 2 liters, no S's here, 2 liters of water, 2 liters of water, and you need to figure out what the molarity of the solution is. So first you figure out the moles of the solute that you have. So to figure out the moles of CaCO3, you're taking the actual mass, so the mass is 50 grams, and you're dividing it by the molar mass of CaCO3, which you can calculate. So the atomic mass for calcium is 40. For carbon it's 12, and there are 3 oxygens, and for each oxygen the atomic mass is 16. And if you add all of that up, the unit of molar mass is grams per mole. If you add all of this up, you would get 50 upon 100 grams here and grams per mole there. And so you can cancel grams and you would get 0.5 moles of CaCO3, of calcium carbonate. And now if you want to figure out the molarity of the solution, what you will do is you will take 0.5 moles from here, and since you're dissolving CaCO3, calcium carbonate, in 2 liters of water, the molarity now becomes 0.25 molars, or moles per liter. And this right here, it represents the concentration. So it means that if you take 1 liter of the solution from any portion you want, let's say those 2 liters were in a beaker, and you take 1 liter of this solution, let's say from here, this 1 liter would contain 0.25 moles of calcium carbonate. And so that's what the molarity basically is. You could have more solutes in that. It's not just for a binary solution, binary meaning 2. You can extend this concept to more than two solutes as well. And while we are at it, while we are taking moles as a measure of the amount, let's also talk about the mole fraction. And the mole fraction is again a ratio. So let's say you have two things in a beaker, A and B, and you have Na moles of A. That's the de facto notation of writing number of moles of anything, and Nb moles, N sub B moles for the substance B. And so if you mix them together, if you form a solution, you form a mixture, then you write the mole fraction, and the mole fraction is written by this Greek letter called chi. It's written chi, but it's pronounced as chi. And chi of A, that is the mole fraction of A, is equal to the number of moles of A over the total number of moles. Total number of moles. So in this case, that would be N of A over N sub A plus N sub B. You can similarly define the chi for B, and that would be N sub B over N sub A plus N sub B. So to take a nice example, let's have 36 grams of water of H2O, and I'm really making up the examples right now. Well, let's have 23. Let's not have sodium. That would react. Let's add to it some 5 moles of A, and also let's add to it. I'm looking at a periodic table right now. I have no clue what to add. Let's add just 24 grams of magnesium, and I'm not taking into consideration how they would react, because if they react, then you essentially reduce the solution into something else, and we are not taking that into consideration. So to calculate the mole fraction, you have to convert everything into moles. So 36 grams of H2O, 36 grams being the actual mass, and the molar mass of H2O of water is 18 grams per mole, 2 from the H's and 1 from the O. And you already have the number of moles of A, that's 5 moles, sorry. And also, when you compute the number of moles of H2O, you would arrive at 2 moles. And for the third part, you are figuring out the number of moles of magnesium. So that is 24 grams over 12 over 24 grams per mole, not 12. 12 is the atomic number, not the mass. So when you divide that, this is the atomic mass of magnesium, and you divide it by the actual mass by it, you get 1 mole. And so if you want to figure out what the mole fractions are for each of these components, so the chi for H2O would be, well, N of H2O, the number of moles is 2, and you're dividing that by the total number of moles. So the total number of moles in this case is 2 plus 5 plus 1, that's equal to 8. So 2 over 8 is the mole fraction, that's 0.25. The chi for the substance A, whatever we have, it's 5 over 8. It's 5 over 8, and that's you can find out it's equal to 0.625. You also can figure out the number of the mole fraction for magnesium, and for magnesium you have 1 mole, and out of 8 moles the mole fraction gives you 0.125. So that's the mole fractions for the 3 components. And one more thing I want you to notice is that the sum of mole fractions, this sigma denotes the sum of all mole fractions, is equal to 1. And that's something that should be pretty obvious, but you can also go on and prove it. You can try just the definition. You can try just the definition of what the mole fraction is, and you can prove that the sum of all the mole fractions of all the components within a solution is going to be equal to 1. So that's two of the concentrations that involve using moles to represent how concentrated a solution is. So we talked about molarity, and molarity is represented by molars. Molars is just moles per liter. That's a better way to remember, moles per liter. And it's just the moles of solute per liters of solution. And for the mole fraction is a unitless. It's a unitless dimensionless number, since you just cancel. Let's say for the case of chi of H2O, you are canceling moles by moles. So you essentially have just a simple ratio that doesn't have any units to it. So hopefully that introduces the concept of mole fractions and molarity. And I would suggest you go on and prove that that the sum of all mole fractions of the components in a solution are equal to 1. Observe it, try to prove it, and I'll see you in the next video.